Okay, we're ready. I did not get the video from yesterday's lecture, so please don't forget to send it to me. And also, what I'm going to do this morning, I'm going to finish the program I was doing yesterday. And after that, I'm going to go to the review. Yesterday, we did the bending, we did the flexion, but I didn't have time to do shear. I did mention to you that chapter G has appeared in the last two codes because shear in the past used to be part of chapter F that deal with beam. And something that I did mention to you that because for Y flange, most of the shearing stresses take place in the web. The nominal capacity is the shearing stress times the area of the web with the modification at the end. So in general, it uses a zero point 0.9 factor. However, most of the cases are going to be in G2. And in G2, you have the P is going to be 1, and C3 is going to be also 1. And in here, there is a user note that tell you which one are the section because most of them, they follow in G2.1 or they fall. This is the problem from yesterday. And the difference with this program was that we needed to find with the shears equal to 0 to find the maximum moment. And in this problem, the weight of the beam was included. If the weight of the beam is not included because we don't know the section, we had to revise the moment and we had to revise the shear. And here we didn't have to revise them. So the maximum shear is 118. We went to chapter 3 and we found from the table CX, the section W30 by 108, and we found this information in the table ZX. And here at the bottom, I checked the deflection, and this formula is at the back of the chapter 3. This was the maximum deflection, and we found the required moment inertia was smaller than the provided, so the section was okay. The next step, I'm going to check shear. I didn't do this yesterday. The design strength has to be larger than the required 118. And like I mentioned before, if and only if we had to revise because we had a new section, this will change a little bit. Also, the moment will change a little bit. This is a question that we just saw in chapter G, nominal capacity 0.6 Fy, the area of the web, and CV1, equation G21. H over TW came from chapter 1. This is smaller than 2.24 square root of 29,050. So phi is 1, C should be equal to 1. The area of the web is the overall depth times the thickness of the web. This came from chapter 1. In chapter 1, don't forget that it has to be in decimal. The thickness of the web has to be in decimal. Here, 0.545. So the design strength, 1 times 0.650, the area of the web times 1, 487.23, much larger than 118. And the rule is that whenever you have a short span, heavy loaded shear good control. But most of the time, you're going to be bending and deflection. This is a typical case that we had a design strength 487, require 118. And I also point out in here that in table ZX in chapter 3, on the right-hand side of the table, This value is given at 487, by computation 487.23. So this is also given in chapter 3 in table CX. Any questions about it? All right, so I'm going to go into the review. I already upload this in Blackboard, and this is a problem from 2016. And whenever you look at these problems, you have to understand scale. And during the exam, the chat is going to be on. If there is a question about the sketch, feel free to type the question. So don't use the microphone. During the exam, yes, if there's something that's not clear, yes, ask me. And here's a 4 8-inch plates are attached to the W10 by 49. So this is the W10 by 49. You can see W10 by 49, and also indicating that this is the W10 by 49. You can see in here, we have one plate on the top, one plate at the bottom. On the web, 2 plates. So altogether, there are 4 plates. And they are 8 inches. I show in here that this is the 8-inch dimension. I also show on the top that this is the 8-inch and 8-inch. So the width of the plate is 8 inches. And of course, we have to use E70 electrode because it's going to be a welded connection. I wanted you to design, or at that time, the people to design transversal and longitudinal weld to safely transfer the load. So I wanted this transversal, longitudinal. I wanted transversal, longitudinal. And the plate 836 for the plate, and the thickness of 3A was given only for the web plate. So you can see the web plate had 3A by 8. This is a 3A by 8. And for the shape, we use A992 grade 50. Also, we needed to determine the minimum thickness for the plates on the top. So all the plates here on the top, the thickness is not given. So that needed to be computed. There's a question from Luke on beams or the review portion. I was finishing the problem from yesterday. Yesterday, I did for the beams, I did bending, I did deflection. Yeah, okay, that was early, good. So sometimes I'm not looking at the two things at the same time. Okay, look, if this is not clear, if the sketch is not clear during the exam, feel free to send me, just type the question and I will give the answer for everybody. Something that always happens. This is given. You cannot change it. And this is already factor. Sometimes it says that it's a service load. This is already factor. And if it's not clear, somebody has to ask me, if is this factor or one factor, but this cannot change. In the exam, the previous exam, I gave you things that cannot be changed, and some people change it. So make sure that you understand. This load has to be transferred. This is the end. This is the end of this girder goes all the way to the right. There's another one on the left-hand side that is not shown, but this is the end of the girder. So the load is transferred, some load by the web, some load by the flanges. I clearly remember this exam that some people decided I'm going to use 50% of the load go through the web, 50% through the flanges, and you cannot do that. The problem is going to tell you how much load is going to go to the web, how much load is going to go through the flange. Any question up to this point? Okay. So what we need to do, we need to find for this plate, we need to find what is the capacity of this plate in tension yielding, because this is the tension. And also in the tension rupture. And at that time, we used to call it fracture. And so I'm going to check for how much load can this plate take in yielding and also in rupture, and we used to call it fracture. What else? What else do you think that I need to check for this plate? What else do I need to check? The block shear is going to be the block shear for the web. So once I decide how much load can be transferred by the web, the difference between the load, the total load, and the load transfer by the web is going to go through the top, to the flanges. And with that load, yield and rupture, I'm going to determine the thickness. And once I have done that, I'm going to check the well, and also I need to check block shear here on the flanges. So the way I started is from I got as much information as I could from the code. This was given in the code was W10 by 49. I found the gross area. I need the thickness of the web. I need the thickness of the flange. And I need the thickness of the web and the thickness of the flange for several reasons. One of them is when I'm going to do the block shear, I'm going to need this information. I'm going to do the shear for the well. For the well, I'm going to find the capacity of the well, the size that I decided. I'm going to check shear yielding and shear rupture. And I need to do shear yielding and shear rupture. I'm going to do not only for the shape, but also for the. And I need to know what is the width of the flange, because I already know that the width of the plate is 8 inches. So for my block shear, I only had 2 inches left on each side. And of course, the properties of the material, FY50, FY65 for the shape, and for the plate, 36 and 58. So this is the way I started the program. For the plates on the web, yielding. And remember, we're doing tension yielding. This is what we did at the beginning of the semester. This is part of exam 1. Yielding is going to be 0.9 because it made out of 836, 36. We had 2 plates. So this is because we had 2 plates. And the dimension of the plate is given. The cross section was 8 by 3/8. The ones in the web, the cross section is given, and you can see in the previous page. So both of them, they will take 194.4 K. I need to do rupture. And so this rupture in here is the phi times FU, also 2 plates. The dimension of the plate is known, so give me 261. It's obvious that in this situation, when I say limit state, for the plate right now, I cannot do anything else. So I found the difference between TU and the controlling. 194 is controlling because it will never reach 261. So 194 is controlling. The difference between TU and 194 is 105.60. This has to be resisted by the plates on the flanges, one on the top and one on the bottom. That's why I use 50%, 52.8. And I went to the flange. The plate in the flange, each one has to resist 52.80 kilo. I did yielding, tension yielding, 52.80 is my TU, 0.9368 T is a no. So if yielding were to control, I need 0.2 quarter inch. If fracture were to control, I have 52.80 equal to 0.75 times 58 times 8 unknown T, T.60. So it's obvious that the largest one control, I have to have a quarter inch plate on the top. Otherwise, it's going to fail. So of these two, 0.20 and 0.16, I went with a quarter inch. Any question up to this time? So I already know what is delta F. Delta F is the difference between the forces. We had a 300. 300 is given. The force they're taken by this plate. The plates in the web, they're taking 194.4. So the difference between the total load and what is taken by the web is 105.6. Well, for T, in chapter 1, yeah, I'm glad you asked that. On page 1-9, chapter 1, page 9. And at the beginning of the semester, I remember I forgot to mention to you to look at chapter 1, page. But here it says, for structural plate, the preferred practice is to specify thickness of 1/16 in increments up to 3/8. Thickness and 1/8 in increments over 3/8 to 1 inch. Right? So, look, for structural plate, the preferred practice is specify thickness 1/16 in increments up to 3/8 and 1/8 in increments over 3/8 to 1 inch. So today, if you have a problem in the exam that you have to select the thickness of a plate, I want you to go to chapter 1, page 1-9, and follow the rule that I just read to you. Okay? All right. So I did forget. What it says? Okay. Okay, so look. Yeah, feel free to ask questions, right? So I started by determining how much force can the plates in the web can resist. So I did tension yielding, 0.936, 2 plates, the web time. These are the dimensions of the plates on the web. So this gave me 194.4. And I did rapture and also 2 plates and gave me 261. So I don't need to go to 261 because this can only take 194. So I decided that what is the load that's going to go to the flanges? The total minus 194.4, 105.6. Then there are 2 plates, one at the top, one at the bottom. Each one of these plates is going to take 50% of the load, 52.80. That's why now I went to the plates at the flanges. I did yielding and using 50% of the load because there are 2 plates. And with this, I found the thickness as 0.2. I did rapture with 50% of the load because there are 2 of them. And it gave me 0.60. Is that clear? Okay. Yeah. So now we do know that the dimension of the plate on the flanges are going to be 8 inches by a quarter inch. So now I'm going to do the weld. And I did the maximum. This is for the web because the plate here on the web, these plates are given at 3/8 by 8. And so 3/8 minus 116, it gave me 560. But I want you to check how do I find the minimum? Well, the minimum is based on I need to weld this plate to the web. So the thickness of the web and the thickness of the plate. The thickness of the web .34. And the thickness of the plate, 3/8. So go to the table. In the code, table J2.4, and somebody asked me the other day this question. In the old time, it was based on the material or the thinner pile joint. Sorry, a thicker. In the old times, in some of the old solutions, it was based on the thicker. Now it's based on the thinner. What is thinner? The plate on the web or the web? And so with that information, is this number correct? In some of the old exams, you're going to find a different answer because we used to do based on the opposite. So right now, I had to make a decision between 516 and 316. I mentioned to you before, I want to repeat it. I just want to have one and only one answer. because there are 60 of you, and I need to grade 60 solutions that they are the same. So I control factor. Sometimes I do not control the factor because you are going to determine there's only one answer that is going to be obvious. But whenever it's not obvious that it could be one, two, too many answers, I'm going to control the factor so there's only one answer. So in this case, I decided to use the maximum. Look, the maximum of 516. I found the capacity of the well by using the 516, the phi, 0.6 of the electrode, 0.707 of the size of the well. So this letter A is the size of the well. 696 per inch. Don't forget to check that computation against the copy, the table that I'm giving to you. So what I did next, I did the shear yielding and the shear rupture for the plate. So we no longer we're doing tension, we're doing shear. Whenever we do the well, don't forget we compare the capacity of the well per inch with the shear yielding per inch and the shear rupture. The smallest number will control our design. So I did it for the plate. For yielding 1 times 0.6 Fy times 3, 8.1 give per inch. Disregard these numbers that I put there, 50%, and disregard that. The rupture, you look at the rupture for the plate and the web, the phi factor 0.6 FU, 38, 9.79. So right now, you compare the 696, A1, and 9.79 for the place on the web. Which one is controlling? The 696, 8.1, 9.7. Which one is controlling so far? Anybody? The well control. But I did also for the web. I did for the web. We have shear yielding one. Now we had a FY50, and this is the thickness of the web. This is given here on the top. The thickness of the web is given here. So I'm doing it for the web 1 times 0.650 thickness of the web, 10.20 kip per inch. And I'm doing the rupture points, the phi factor 0.6, 65.34, 9.94. Now, if I compare the capacity of the well per inch and for the web, the shear yield and shear rupture, what is controlling my design? Or what is still controlling my design? Anybody? So what is still controlling my design? The well. And so the well is controlling the design. But I put a note in here. And I'm going to go back to this before I go to my note. Right? I'm going to have well on this side. I'm going to have well also on the other side. So I want you to look at this. This is the web. I'm having well on this side. I have well on that. So the capacity of the well, what is resisting by this web, is going to be twice the capacity of the well. So if you look at this is the web, 2 plates. I have weld in here, weld all over. So I put a note. And this is the note at the bottom of the page that the web cannot receive 2 times 6.96, 13.92. Why? Because look at the capacity of the well, 10.2, 9.94. So what I did, where did pointer Edgar Hernandez? I will kill you later. No, don't worry. I'm just kidding. I'm kidding. Look, page 1, W10 by 49, the area, the thickness of the web. Edgar, you get that? Yeah, don't worry. You're waking all of that stuff. But don't forget that there are 2 portions. One is in decimal, the other one, this is the one for you. I know you're familiar with it. Hey, please feel free to ask any question. There is no bad question. All of them, there are good questions. So, I'm sorry I made fun of you, but ask any question, please. So what I was saying is that since we have the web is resisting well from both sides, what we really have is 13, instead of 696, has to receive 13.92 kip per inch. And the capacity is 10, 20, and 994. So it will fail. So I decided I'm going to use the minimum one. And the minimum size of the well gave me 4.18. And I did a computation, or probably I just got it from the table, 4.18. And 4.18 times 2 is 8.36. So there's no problem in here. Any question up to this point? So you understand that I had to change the size of the well because that web is going to fail. So I decided to go with a medium. And now, look, total length times 4.18, 97.20. Where does that 97.20 come from? I'm doing the web. And whenever we go to the web, this is what I did before. The web, the plate web, they had both of them receive 194.4, 50%, because there are two 50%, 97.20. So that 97.2 comes 194.4 divided by 2, and this is what I have in here. The total length, 4.18 kip per inch, and the total length equal to 97. This is for one plate. So the total length was 23.25. So this side, this is the plate. This is the plate on the web. It had 8 inches. So obviously, I'm going to put 8 inches of well. So the difference, the total 23.25 minus 8 inches of well, it gave me 15.25. And so when you divide 15.25 by 2, it gives you 7.625. Since we're using the half an inch increment, I went to 8 inches, 8 inches, 8 inches, 8 inches on each side, because these are the plates. Yes, I divide by 2 because there are 2 plates. Yes. Any question? Any question? So this is what I have on the web. So right now, here on the web, I had 8 inches, 8 inches, 8 inches of well. So on this side and on that side, I already had determined the well. So this is what I have, 8, 8, 8. What else do I need to do? What else do I need to do in here? Well, look, I had longitudinal and transversal. Longitudinal and transversal, well, the same size, 316, 316 size. And the load is applied at the centroid. What do I have to do in here? What does the code tell me whenever you have longitudinal besides block shear? The code said, yes, whenever you have longitudinal and transversal, well, you have to check, assuming that the capacity of the transversal well is 50% stronger, so 1.5. And assuming that this longitudinal are 15% weaker, 0.85. So where in the code is that equation? What page in the code is that equation? Excellent. And these are equations, and that is the correct page 16.1120. Whenever I'm solving a problem, and look, all that we have is time. We have plenty of time. So whenever I'm solving the problem and you don't know where I'm getting the equation, just stop me and ask me. This is the 0.85 and 1.5. So here on the top, 8 million because I'm max. Okay. There's a question from Adrian. Why do we go to a minimum? And so the answer is here. We did the capacity of a 516. We start with the maximum. The minimum is 316. Right? So I compare this capacity of the well per inch with the shear yielding and shear rupture of the plate, shear yielding, shear rupture of the web, and this was the smallest. However, I was saying that the web is going to resist the shearing stresses from two plates. So what the web is resisting is 6.96 times 2. 696 and 696, 696, 696 times 2. And this is what I did in here. I put a note, the web cannot resist 2 times 696 because it's 13.92 kg per inch. The maximum capacity really is 994. That was the reason why I changed to the minimum. Adrian, did that answer your question? Never mind. Okay. All right, good. I didn't see the never mind. Okay. So that was the only reason. But we need to do the second equation because we do have longitudinal, and transversal wells. So due to research, now we know transversal wells are stronger than longitudinal. So I had to increase by 1.5 the transversal 6.27 and reduce the longitudinal. So I multiplied 627 times 8, gave me 5016. The difference between 97 and 5016, 4704. So I divided 4704 by the 355, gave me 1325, 7 inch each. So I had 316 with 7, 316 with 8, and 316 with 7. So the next step is to do the block shear. And the block shear is going to be for the web. So whenever we look at the web, this is going to be the block shear, the U shape. So there's no block shear for the plate. It's going to be a block shear for here for the web. So the thickness of the web is given here on the top, the point 34. So the block shear in here is going to be simple because for the gross area in shear is also equal to the net area in shear because no hole. 2 times 7 inches times the thickness of the web 4.76. The net area in tension is also equal to the gross area in tension because there's no hole, 8 times 0.34. And this is the same equation, 0.6 FU, because it's the web. And FU times the net area in tension, 0.6 FY. This is the same block shear equation we always use. So we had 239.70 larger than 194.4. Why comparing with 194.4? Because 194.4 is the force that is going to be transferred by the web. Any question up to this point? So the block shear is for the web, and it had to be compared. This is the 194 that is resisted by the web. I saw we're going to use the right side of that equation. I saw we're going to use the right side of the equation. Just a minute. This is from no, this is from Celeste. She thought that we only use the right side of that equation. This is the block shear equation. Right? And please feel free to ask questions. This is the best time to ask questions. And let me tell you, if you are embarrassed of asking questions, just later, save the question for later. And if you want privacy, just send me a email and you have privacy. But feel free. This is a typical equation, as you know, that appears in the code. It says that nothing can be larger than this value, but this value can be smaller than that. So you do have to use both sides of the equation, but nothing can be larger than this value. And yeah, the 418 is in the table. Check, I don't have the table with me. You, Edgar, you don't have the table? It's not in the code, it's a table I gave you in class. Ah, okay, okay, good. All right. So please ask questions. So I'm going to go to the flange. We already determined that the thickness of the flange is a quarter inch. We determined this before. So the maximum size, a quarter inch minus 116, 316. And so I found the minimum 1/8. So I decided to use the 316. And now I did compute it, and here I didn't use the table. 0.75 times 0.6 times 70, 316, 418 kip. The same number that I had before. I had to do the shear yielding and shear rupture. And here I did shear yielding for the plate and shear rupture for the plate. So we had 4.18, 5.4, 652. I said they were. Why? Why I didn't do the shear yielding and the shear rupture for the flange? Anybody? Flange thicker and also a stronger material, right? So during an exam, when something is obvious, and remember, time constraint. So whenever you had a time constraint, something obvious, you just write a note. It's obvious. That's what I'm not doing. At least I know. But don't waste your time because you have 1 hour. You have to upload your exam. So I didn't do the flange because of the reason that you're saying thicker and stronger. So 4.18 times L, 52.80. This 52.80 kip is the same that I used before to determine the thickness of the plate. So in here it comes at 12.63, 12.63 minus 8 because the width of the plate is 8. It gave me 2.5. Very small 2.5. And I have to compare this with the minimum length. In the code, it says that four times the size of the well. Where in the code we can find that? What page in the code? It says that it's 4 times. What page? Page 16? Oh, what? What is it? The page 16? 120. Okay. All right. So everything is given in the code. So because it came too small, I decided to check. It was okay. I had to do the second equation because we had longitudinal and transverse. And also, when I'm looking at this, I'm saying I could have a problem with a block shear. I'd have a problem. So with this too small, I said, oh, maybe the block shear is going to fail. But I need to check the second equation. 1.5 transversal stronger, longitudinal weaker. So I multiply the 627 times 8, it's 50, 16 kip. The difference is only 2.64. $52.80 right? And I put this on the other side, 2.64 kip, 2.64 kips divided by the capacity 350.7, 50.5 inches each. No good because 4 times 316 is 0.75. So what I did in here, I kept the old solution. A 2.5, 1 and 1. Where does this 1 and 1 come from? Look, how do I know that it's 1 and 1? No. Don't worry. This is the width of the flange in chapter 1, 10 inches. Yeah, good. Look, 10 inches. Right? So what I left, I had 10 inches minus 8, 1 and 1 on each side. And the length is 2.5. So the block shear is going to be 1 times 2.5. So there is an L in here and there is an L in here. Because the U is not going to happen because we have the web. So if you look at this, the U is not going to happen because the web. So we're going to have a double, a L and an L in here. And this is what I have. So for the block shear, it's going to be 1 times 2.5 is not to scale. Look, the 2.5 cannot be larger than that, is not to scale. But it's 1, 2.5, 1, 2.5. And this is what I put on the next page. On the next page, block shear, 2.5 and 1, 2.5 and 1. So, like I said, the U is not going to happen because that portion of the flange is connected to the web. But we're going to have the outside of the flanges resisting the block shear. So the gross area is 2 times 2.5 times 0.56. This is the thickness of the flange, 2.8. The net area in tension, the same as the gross area in 2 times 1 times 0.56, 1. I did the block shear the same way that we always do, and it came 117.6 is larger than 52.8. Okay. Any questions about this problem? Why wouldn't we do summation of x moment to see the web at the beginning? Summation of x and moment to see the force applied to flanges and web at the beginning. Oh, this is the beginning. Uh, we only balance whenever we had an angle. Whenever we had an angle, I'm gonna put the angle in here. I'm making this up. I just want to answer Stella's question. Right? This is an angle. This is a gossip plate. This is the connection. And so the law has to be applied at the centroid because if the law is not applied at the centroid, this will become a eccentric shear problem. So this is what they call concentric. Concentric because the law is applied at the centroid. If I apply, I'm making this up, these dimensions are just created. 4 plus 2 is 6. If I put it away from the centroid, this is eccentric shear problem. So this is concentric applied at centroids. In these are different dimensions. We're going to have a force in here, F1, a force in here, F2, and a force here, F3. To balance, to be in equilibrium, F1 is going to be different than F3. So the length of these welds are going to be different. In our case, everything is concentric. So these lengths are exactly the same. That's why we don't have to do what you. They already balanced by itself because this force and this force are exactly the same. And we just wanted to look at what's sure. Okay, good. Thank you for helping me. All right. Any other question for Luke? Any other question? Will you go back to the last page? Sure. Okay. I'm here. For this, can we use the word table you gave us? Okay. And this is ice, right? Look, ice. Uh, before the spring break, we were living in a different planet. Everything was different. Now we are in a situation that we cannot leave our homes. We don't know if we're gonna be dead tomorrow. Everything has changed. And so before all of this happened, I said in class for exam number 2, do the computation, and after that, use the table to check your number. But now everything has changed. So yesterday I said it's going to be an open book, open notes. Get any solution manual because you're not going to find my exam solution. So you can use the table now, but it's a good practice to do the computation by hand and check the table. But everything has changed. Any other question? Okay. Anything else about this problem? And I tell you, a lot of people got this problem wrong because they didn't read the problem. They didn't understand how the law were transferred. And also, we have to be careful whenever we had a well, capacity of the well per A compared with the shear yielding of the base metal and the shear rupture of the base metal. The smallest number control. Most of the time, it's going to be the well. But sometimes we have to be careful. Like in here, the web was the problem because it was resisting well from both. Okay. Any other questions? So I'm going to go to the second problem, and it's 929. I'm going to jump to a column and come back to the second problem. Second problem is also well. Several people asked me about a problem like this one. So we always check shear, yielding, and fracture between the shape and the wall. Right. Then, well, we had to check the like whenever it's not obvious, like at first, I check the shear yielding and the shear rupture of the plate. And also check the shear yielding and the shear rupture of the web. And the reason why I did both was because we needed to know which one was the smallest, but also because the web in this particular case, the web was the critical one. No matter how strong the material is, we had a situation where we're getting twice the amount. So the thickness, the smallest thickness control, according to your question, if the smallest thickness has the, the weakest material, obviously it will. Any other question about that last one? Any question? I was saying that several people asked me about this. The design of the column is simple. We had the column table standard forever, W8, W10, W12, W14. You can close your eyes and solve the problem. Those are standard shape. However, what about we have one that is not in the code? Right? In here, we had an axial load, 1,000 kips, sorry, fixed support at the bottom, pin at the top, 18 kips. No brace in between. So in here, KLX and KLY, they're exactly the same. The light is W18 made of A992 raised 65 steel. The factor axial load is 1,000 kip. And the column is fixed at the bottom and we use the specification. So we know that what is the K value for this situation, KX and KY are exactly the same. What is the K value that we have to use? 20. And that point A, which table? Where is the table that given it what page? Good. So we're going to have KLX and KLY. To select a W18, we're going to go to chapter 1. So on page 122, go to that page. In order to solve any column problem, we have to know the KL over R that is going to control our design. KL over R in this case, because there's no brace, KL over RY is the critical. So the only thing that I need is Y to start my computation. So what I used to tell the people, look, I asked in class, how old do you think that Dr. Diaz is? Write a number. How old Dr. Diaz is? Wait, oh man, I'm gonna tell him 18, he like that. He's closer to 70, right? So you start because you like Dr. Diaz, you start W18 by 70, right? And there is a guy in the class that likes older women, 40, 50 years old. you start with W18 by 40 feet. Or there's a lady in the class that, like older men, you start with W18 by 100, right? And if you don't like anything else, you just close your eyes and put your finger in there, right? So any way that you want. So the only thing that we need to get is the K over R. It's gonna tell me if I should go to heavier or lighter. Okay, so that is there's no magic any way that you can. So I decided to use everything by 106 because my grandfather lived to be 106 years old. That's the only reason, right? But the point is that you select any section that you want. So I selected everything by 106. In chapter 1, it gives me gross area, B over 2 times the thickness of the flange, H over TW, because I have to make sure that I don't have a lender section or local back. And here on the top, I have KLS, KY, 0.8 and 18, 14.40 feet. You already told me 0.8, 18, B over 2 times the thickness of the flange, H over TW for 65, 1183 and 3147. So 1183 and 596, okay. 3147, 27, okay. No local body. Eh? Well, I don't know what table you're talking about because we don't have a table with W18. So K over RY. K over RY. It has to be in inches. I always repeat it, inches, because many of you forget to multiply times 12, and you're going to get the wrong answer, 64.96. So in here, can I use the table at the end of chapter 4? And the table at the end of chapter 4, they go all the way from, look, from 35 to 70. So I could use this table. I could use this table because the way they computed this table, I already have shown it to you. They use the equation in chapter E. But I decided to use the equation just to show you. So since 64.96, that is K over RY, this is more than 4.71, 29,065. This is inelastic, but this is the equation in chapter E. This is the Euler equation, pi squared 29,000 K over R, 6783. I put it in here, and it came 0.9 times 41. This is the area. So the stress times the area, it gave me, sorry, this is the 0.9 times the stress, and the stress times the area. So we had the area in here, we had the stress in here, the stress times the area, 1175.58. This is okay, but it's not the best one. We need to check if this is the solution or we had another one. So I have to go to chapter 1 and look at the W18. So in chapter 1, W18, the W18 by 106 worked. which one is the next one that I need to check to make sure that this is the best section or is not? The W18 by 106 worked. Which one is the next one that I need to check? I go to chapter 1, which is the next W18 by what? Correct. We had W18 by 106 by 97. No, we need to go one at a time. 97 because we're close. So I want to check the W18 by 97. Gross area, RY, B over 2 times the thickness of the flange, H over TW, the same that we always do. KL over RY, 65.20. So the same equation control in elastic back. The same equation with 65, he gave me, and this is the Euler formula, he gave me a stress, critical stress 39.05 times this, 1112.95. This one, it works. What is the next one that I need to check? Yes, 86. 86, I want you to pay attention because 86 is one that we're going to have problems to check this one. But there are two ways. I'm going to do an approximation, something that is logic, and after I'm going to show you how to compute the critical stress because somebody asked me in all the classes, so I did this to answer your question. W18 by 86 doesn't have anything in here on the top that tell me that there is a problem. There's not a letter C, there's not a letter F, there's nothing in here. So this information came from the code. Gross area, B over 2 times the thickness on the flange, H over TW. It came that the web is slender. So the web is slender. So whenever the web is slender, it's going to reduce the critical stress. The way we compute the critical stress is going to be reduced. But I'm going to assume that this doesn't happen. And later I'm going to check. I'm going to assume that this is not happening. So I did a K over RY, 6570, is smaller than 9949, the same formula as before. And so I computed this as 4241, the critical stress 38.16, 38.16 times the area, no good. It's smaller than a touch. And I also went to this table at the end of chapter 4 between 65 and 66 because KL over R is 65.70. 65.70. So I came here and said 65 and 66, my critical stress 38.85. Very similar to what I obtained in here. So look, assuming and ignoring this problem, I'm ignoring this problem here that there's a problem with the web. Ignoring that, give me 965.44. No good. If I do the exact computation, considering the problem with the web, what do you think they're going to obtain me here? Is smaller than 965 or larger? Less value, it's more. So whenever I do this, I stop it here and I conclude if I do the exact computation, it's going to be smaller. However, because somebody asked me, I put a note in here, it's going to be much smaller. Somebody asked me, I'm going to do it. So I had to go to E4. And E4, I had this equation that I used the other day for the Euler whenever we had twists. And this equation is much easier today because in chapter 1, for this section, besides IX and IY, J is given in there. C to W is given in there. G is given in chapter E, and E4 is given in there. So I computed this value. This L to CX is exactly the 14.40. You need to multiply times 12. And let me check this equation. Yeah, this is the equation that I'm talking about. This is the equation that I used the other day. And the square is missing in here. In this portion of the equation, the square is missing, but the square is in here. So this F to E, 103.39 came larger than 66.31. This 66.31 is the Euler elastic that I computed before. So the code says that you have to use the larger 103.39. I put in the same equation and it gave me 30 point as a critical, it's 30.06. In the code, in E7, somebody asked me the other day, can we use this for the web or for the flanges? And I said, yes, now I'm using this for the web. This affected area is the reduced cross-sectional area. There is a limitation in E7. A lambda is smaller than lambda sub r multiplied by Fy over the critical. There is no change in the B. In this case, the B is the age because we're doing the web. So in this case, this is what I did. This in here give me 33.4 is more than 43.48. No change. So the exact value is 760.57. The approximate value was 965. But either, then it doesn't work. So the answer to this problem is the 18 by 97. Any question? Lambda. Okay. In chapter B, In chapter B, this is the table that we use for compression. We have right now is compression. So B over 2 times the thickness of the flange is the lambda. The lambda sub R is whenever this is the value of lambda sub R 0.56 E equal root of Fy. This is for the flange. And this is the lambda for the web. And this is the lambda sub R for the web. Any other question? So the point that I wanted to make in here is that when I check the next section, the W18 by 86, when I checked this section, we knew that we had a problem with the web. I ignored it. I assumed that there was no problem. I did the computation the same way that we always do. And it came, there was no good. So if I would have computed the critical stress based on the problem with the web, even if I did that, it would have been even smaller. Either way, it doesn't work. And I also below here, I wanted to show you that we could use to compute the critical stress, we can use the end of chapter 4 because it's good between 5 and 7. Any question? I want to answer the other question from Luke. And I don't want. Look, can we do that in the exam or you want us to do the calculation? Of course, you can do this in the exam. Of course, it's showing me that you really know what you're doing. So whenever you do this in the exam, I expect you to put a note like this. Assuming that flange is okay, if flange is a lender, assuming that the flange is okay, doesn't work. But in the flange is a slender, this value is going to be much more. That's what I want people to do, to show me that you understand what you do. Luke is asking if A92 grade 65 in chapter 1. This is from an old exam. And let me check. Chapter 2, you mean? Is that what you mean? Chapter 1 or chapter 2? Look. Chapter 2. Okay. So in chapter 2, we had this is a table for structural shapes. Right? So in this table of structural shape, you should find everything you're looking for. And this was from the old code, A92, A992, A992, grade 65, A992, A992. It's not in here. So if it were today, I give you another one with grade 65. But grade 65 means no matter what type of steel, 65, KSI, this is the FY. Any other question? Can we do this? No more questions. Okay. I'm going to go to the next problem. It's only the combination of LCX is only for the Y shape. the computation of, no, LCX or ICX. FOMO, what do you mean LCX? Or LGX or LGZ? You Are you asking about this one? FOMO. Yeah. Well, it's not. We only had, this is the torsion. The one that goes in the formula is the Z, because the Z is the torsional axis, the longitudinal is the torsional. So this is the Z. Is that what you're asking for? Ly? No, so what are you asking for? So what are you asking for? LCX, LCY? LCX. Okay. Look, when we start talking about columns, I mentioned that now the code has the effective length L to C, and the L to C could be either L to CX or L to CY, depending which axis control. But this in here, LC over R, is the KL over RX and KL over RY. The only thing that they had done, the code, this KL, they're calling it now L to C. But we had, for the column, is the strong axis control, KL over RX, is going to be, this is the KLX, and if the weak axis control, K over RY, this is going to be the KLY. And if we have torsion, it's going to be KLZ. Is that what you wanted to know? Okay. Any other questions? Yes, the smallest. The smallest, because whenever we have a problem with a flange or a web, it's gonna reduce the design strength. So if we compute the design strength for a column based in lateral or flexural back, and we computed based on torsional backlink, the smallest number control. In the code, whenever we had to compute the same, the capacity based on two different conditions, the smallest one will control. Any other question? I don't think that I missed any question. Okay, we're gonna look at this problem. And remember, I've given you the table, and the table, they treat the group of well. Look, there's a well, a 3-inch, nothing in between, 3-inch, 3-inch and 9 inches. The eccentricity, this force in here with 75 degrees, you're gonna have a component vertical going down, you're gonna have a component going to the left. And the eccentricity, this distance is 6 and this is 9. The table that I'm giving to you, it treats the wells as lines. And that's why if you look on the top of the table, it says inches. The polar moment inertia is inches to the third instead of inches to the fourth. So we represent this with this little rectangle, but in reality, it's a line. A line doesn't have the dimension. But if we use two dimensions, B and H, that's the way we're going to do it. So there is only one bracket. Sometimes there are two of them. They want to find the well size and the minimum plate thickness. 836 for the plate and 870 for the electrode. So like any other problem, we have to find the location of the centroid. And so I can use as a reference this line. I can use as a reference this line, anything to find the vertical axis. I need to use probably this as a reference. To find the horizontal axis, I could use this as a reference or that as a reference, normally either top or bottom. I think I use the bottom. So I'm going to find the location of the centroid. Let's say the location of the centroid is in there. From the location of the centroid, I'm going to apply moment about this point and find mu. I'm going to transfer the vertical and the horizontal component of that force to the same location. So I'm going to have direct shear on the y direction, direct shear on the x direction. And the moment is also going to create forces. They're going to have a component in x and component in. The critical point for the moment is the one the farthest away from the centroid. But the farthest away from the centroid has to have a component in y going down, a component in x going to the left. So we can add those to the direct shear. The polar moment inertia about the x-axis, polar moment inertia about the y-axis. So I have to find the centroid first. Any question about it before I start showing it to you? And this is a case of eccentric shear. We had eccentric voltage connection and we had eccentric welded connection. So to do this, they want to know the size of the well and the thickness of the plate, E70. So what I did in here to start with, I found the component of the force in the vertical direction going down 67, 61. In the x direction, horizontal to the left, 18.11. So the component from the moment that one the farthest away from the centroid, it has to be down, has to be to the left to find the result. So I have found in here, we refer to the right side. So my X bar, we refer to this side. And I started with this one. It's a line. 3 times 1 times 0, because it's a line. I got it in here. And I put the area at the bottom. After that, I had this one on the top. This one on the top, that is 3 times 1. The centroid from here to this line is 1.5. That's why I have it here 3 times 1 times 1.5. And I put it here at the bottom. After that, I got this one, 3 times 1, and this distance from here to this side is 3 plus 3 plus 1.5, 7.5. And I put it here at the bottom because the summation of area goes at the bottom. And this one in here is 9 times 1. The reference from here to here, 4.5. 9 times 1 times 4.5. I put the area at the bottom. And it came at 3.75 inches from the right. So the location of the vertical axis, 3.75 from the right. Any questions about this? So that had located my centroid 3.75. So this distance from here to here, 3.75, I had located this axis, 3.75. Now I need to locate the horizontal, and I use this as a reference. So to find the y, you can see I'm using the bottom as a reference. So I had 9 times 1 times 0 because it's a line. Summation area, this goes at the bottom. After that, using these two here on the top, 2, 3 times 1. This distance from here all the way to the centroid, that is this line, is 9 plus 3, 12. 2 times 3 times 1 times 12, because this distance to the line is 12. Two of them here at the bottom because I measured the area. Plus, I had this one, 1 times 3. The distance is 9 plus 1.5, 10.5. 10.5, I didn't write it. 10.5 over the summation area. It gave me 575 from the bottom. So this is located 575 from the bottom. It is located at 375 from the right. Any question? So the location of the centroid is easy. If you had a case that is in the table, feel free to use the table. If the case is in the table, you have a copy of the table. If you cannot find your copy for any reason, just let me know and I will send you one. But if and only if the case appears on the table, you can use it. So after that, what I did, I played with the geometry. Location of the centroid, 3.75. Location of the centroid, 5.7. So the distance, this is 3.75. I need a distance from this area, for instance. This distance from here to the centroid. So since this is 3.75, this distance is 3.75, and I need this distance. I did 3.75 minus 1.5. So 375, locate this, 375 minus 1.5. Tell me, what do you find? Do the computation. 375 minus 1.5. What does it give you? 3.75 minus 1.5. Anybody? 375, 2.25. Okay. And this is exactly what I have in here. Look, 2.25. 2.25 from this centroid to this line. I'm going to do the same for this one, but this one is a line. So what is the distance from here to this line? What is the distance? The distance from here to this line. What is the distance? From here all the way to this line. It's not 3. It's larger. Is this distance? Look, what is this? 3.75. Right? 3.7. Now I want to do this one. I need a distance from this centroid to this line. I need this distance, look, from this line to the center. So how can I compute that? Look, I have this distance. This distance is 3. This distance is 3, 6, 7.5. 7.5 from this side is 3, 3, and 1.5, 7.5. And I need the distance from here to this line. So 3 and 3 and 7.5, what do I need to subtract from 7.5? 3.75, it gives me 3.75. That's correct, 3.7. This is the last one that I need. Look, the vertical axis is 3.75. The centroid of this is 4.5. So 4.5 minus 3.75 give me 0.7. So I had all these distances. Now I need the distances, for instance, from here to this line, this distance from the horizontal to this line is 5.7. The distance from here to this point, so the distance between this horizontal axis and this centroid is going to be 6.25. This 6.25 is the total, this total distance. This total distance in the previous page, this total distance is 12. So 12 minus 5.75 give me 625. 625 minus 1.5 give me 4.75. This is 1.5. And the distance from here to here is also the distance from here to this line, and from here to this line, the distance from this axis to this line is what? Anybody put it? Distance from here to here is what? Distance from here all the way to the top, write it number 620. So we already had the geometry. I'm going to find the moment first. The moment we had two forces, 67.61 and 18.11. I need the distance, 67.61, the distance from this line all the way to here. So this distance from here all the way to this line is the 6 inches. 6 inches plus this distance that is 1.5 plus this distance that is 3.75. So for this force, I had this distance that is 6 plus this distance that is 1.5 plus this distance that is 3.75. So the force times the distance. For the horizontal, 18.11 times this distance, 6.25. Since both of them go in the counterclockwise direction, my MU is 878.18. 0.88, sorry. On the counterclockwise. We always leave this and keep inches. Always this moment. We never convert this into keep foot. This is one of the few times that we leave this keep inch. I'm going to do the computation of the moment inertia of all these lines about the x-axis. So here on the top, I had two of this. Lower this a little bit. Here on the top, I had two of this. Now I put two. The moment inertia of each one of them is the base times 1 cube over 12. I told you that we just given a dimension to be able to say b h cube over 12. Every time that the 1 is to the cube, we're going to throw it away. What is large is the area distance squared, 1 times 3 times this distance, 6.25 squared. Plus now I have this area, the base 1 times 3 cube. The base 1 times 3 cube over 12. Plus the area, 1 times 3, distance squared, 4.75 squared. I had taken care of those two areas and this area. Now I have this one at the bottom. They're going to be the base, that is 9 times 1 cube over 12. 9 times 1 cube over 12, because 1 is to the cube, I throw it away. What is large is the area, 1 times 9 times the distance squared, 5.75. So moment inertia about the x-axis, 6 or 1.875 inches to the third, because this is a line. Inches to the third. The table given to you also says inches to the third. Every time that we work, it's going to be inches to the third. Any question about how to compute ISO X? I'm surprised, no question. Everybody's sleeping. Everybody leaves the room, already left. Okay. So this is the way every time B8 cube, whenever the 1 is to the cube. I know that it's not, sometimes it's not that insignificant, but it should, because this dimension doesn't exist. We're going to find the moment inertia about the y-axis. So it's going to be the base times height cube over 12, area distance squared. The base times height cube over 12, area distance squared. The same in here. And this is going to be the base times height cube over 12 and distance squared. So this is what I did here below. I to y. This one in here. This is the base for this one. 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 So 1 times 3 cubed over 12 is given in here. 1 times 3 cubed over 12 is the moment inertia about own central axis. 1 times 3 cubed over 12. Plus the area, 1 times 3 times the distance squared, 3.75 squared. So the moment inertia of this one is 1 times 3 cubed over 12. Give me the moment inertia about this line, plus the area times distance squared. This is the distance squared. This is what we had in here. This one in here, 1 times 3 cubed over 12. 1 times 3 cubed over 12. Plus the area, 1 times 3, distance squared. This is the distance you gave me before, 2.25 squared. In here, we had 3 times 1 cubed over 12. Moment inertia about this line, but this is a line that goes away, 1 cube. Plus the area, 1 times 3, 3.75. This distance is 3.75. That's why 3.75 squared plus 1 times 9 cubed over 12 plus the area times 0.75 squared. All of this give me 169.875. So whenever we add I to x and I to y, give me I to p, 771.75 inches to the third. Any question? We had I to p, now I'm doing R to bx. And several people have asked me about this. So I just want you to go to chapter 8. And in chapter 8 on chapter 8, page 12. Go to chapter 8, page 12. Several people asked me about this. Before the spring break, I mentioned that you should do this. In here, I want you to put, instead of this, put Rx is equal to Px over L. And Ry is Py over L. So I want you to write in here what I'm going to do right now. This is the direct shear. The force divided by, this is the total length of the well. So for the X, I want you to write Rbx is equal to Px over L. This is the direct shear Rbx, Px over L. And Rby, Py over L. So this is the direct shear in X, direct shear in Y. This is the total. This is the total length. And in the next page, in here, they give you the X and the Y. This in here is MU. And this is the Y distance. This is I to P, I to X plus I to Y. So the way I usually write this, I put R to X is equal to MU times Y over I to P. MU times Y over I to P. The component in X goes with the Y value. And the component in Y, Ry, is going to be MU X over I to P. So this is what I want you to write on that page. So going back to the problem, the component in Y, 6761. The component in X, 18.11. How many inches of well we had? 3 plus 3 plus 3 plus 9. So here on the bottom, component in X, 1811 over all the length of the group of well, this 18. So give me 1.006 kip per inch to the left. The component in Y is the force in Y divided by how many inches for well we had, 3.76 down. So 3 plus 3 plus 3 is 9 plus 9, 18. 6761 divided by 18, 18.11 divided by 18, to the left and to the right. This is what I have at the bottom of the page. Direct shear in X, direct shear in Y. You see the moment in here. And for the moment, for instance, this is the force produced by the moment at this point had a component going up, a component to the left. This is the force at this point, one component going down, component going to the left. This is the force in this corner, component to the right, component down. At this corner, the force produced by the moment, this is perpendicular to this line, component to the right, component. This point, the coordinate of this point in x, 3.75, in y, 6.25. And this point, the component in x, or the distance 5.25, in y, 6.2. If you compare these two critical points, because the farthest away, this force is opposite to this. This force, the same direction. If you look at this one in here, this force goes down, this force goes to the left. Which one is the critical point? This point on the right or this point on the left? Anybody? Left. The left. Okay, so I'm going to compute the moment, 873.88. When I find the component in x, I'm going to use the y, 625. When I find the component in y, I'm going to use the x, 5.25 divided by I sub p. And I sub p is given in here. So on the next page, and this is page 9 of 18. On the next page, I computed the component in x due to the moment times the y distance, and this is log. This is the y distance over I sub p, I sub x plus I sub y. It gives me 7.08 kip/inch to the left. The component in y is the same moment, but this is the x distance from here, 5 to 5. Divided by the polar moment inertia, it gave me 5.945 down. I have found the result at 0.1. All the component in x plus all the component in y squared give me 12.63 kip/inch. I need to find out the size of the well. So I put 12.63 is equal to 0.75 times 0.670, 0.7078. 8 comes up 0.57. So I try to find the size. If I have a 916, it's 0.525. If I add one more 16, 10, 16, 8, 0.625. More than this. It has to be more than this value. That's why I selected a 5.8. And so the capacity of 5.8 is 0.75 times 0.6 times the electrode, 0.707, 13.92. I need to compare this with the shear yielding and the shear rupture if I do have information. But the thickness of the plate, that is one of the questions. To find the thickness of the plate, I had the size of the well plus 116. Because remember, the maximum size is the thickness of the plate minus 116. So I'm adding 116, this is the plate. Now that I know that the plate is 1116, shear yielding 1 times 0.636, 1116, 1485 kip/inch. Shear rupture 0.75 times 0.658, 1116, 1794 kip/inch. Compare 1392, 1485, 1794. The well is still controlled. So the answer is the plate is 1116, the size of the well 5.8. Any question? Can you move the paper up? Yes. Okay, let me tell you. I'm going to go back to this. So we found the component of the force due to the moment. This is the moment. This is y. The distance y is I sub p 7.08. The component due to the moment, the y direction is the moment mu. This is the x over, 1 is the critical point. We discussed before, 1 is the critical point, and this is the x value, and this is the y. So what I did, I computed the forces due to the moment. I was saying this is mu, this is y, and this is I sub p. Give me 7.08, keep to the left, the same direction as the other one. And in the y, this is the moment, this is the x from the previous page, I sub p given. So I found now the resultant at point 1 that is the critical. Summation of the component in x squared plus summation of components in y squared. Give me the resultant. This resultant force at the critical point is 12.63. I'm finding a well that had this capacity or more. So I came here and I found that the well is 0.567. I had to get a standard size of the well. So I said a 916, give me 0.625. It's smaller than this, but I'm close. So I add one more 16. 16 plus 116, 1016. This is 5.8. 0.625 is more than it. So the size of my well is going to be 5.8. And the capacity is, now that I had 5.8, I find the capacity is 13.92 kg per inch, more than what I need. More than what I need, it's good. I need to find the plate. And remember, if the size of the well is 5.8, the plate is going to be 116 thicker or larger. So to the size of the well, I'm adding 116. So my plate is 1116 plate. But I had to check shear yielding and shear fracture because we cannot exceed those values. And here is shear yielding, 1 times 0.6 Fy, 1116 give me 1485. It's smaller. This value is still smaller than this. And shear fracture 0.75 times 0.658, 1116, 1794. Still, this is smaller. So the well is still controlled. So the answer is 1116 plate and 5.8 well. Okay. Any question? Any question about this problem? So all these problems are very similar. You have to be careful locating the same drawing, computing I sub x and I sub y, and after that you have to find the critical. And the critical is the one that had the largest force. And remember, whatever we do, if we have the information, we need to check why we add 116 several locations. This is page, chapter 8, page 36. You see, I don't know who has it. Ali, look, I had the size of the well. I need to add 116 to have the plate. Ali, this, okay. Any other question? The well equation we use in different web page in the code, the well equation we use in different. Okay. remember that this is page 16.1, 124. Right? And remember that no matter what we do, feel left well, always assume that we're developing sharing stresses on the effective area of the well. So in here, they tell you the feed factor 0.75, the nominal capacity of the well 0.6 of the electrode. And on page 16.1, 122, this is the equation that we use. Instead of using the area of the well, the area of the well is 0.707 A times L. We have written this, we had to have it in kip per inch. So what we have this equation for LRFD PR squared of the well is 0.75 times what? What else for that equation? 0.75 times 0.6 of the electrode times what? 0.707A. 0.707A, nothing. So this is the equation that I'm using in here. This is phi, this is 0.6 of electrode, 0.707 of the size of the well. And we had the answer in kip per inch. Everything we do in kip per inch. The same, this equation, kip per inch, we are not multiplied times. Any other question? Are we like going to have this type of well problem or like the first one of the exam? I don't know. I don't know. I will give you more information. Here again, we always using this morning thing. Yeah, we decided that because the code is not clear about which one is the base method. Whenever we using shear yielding and shear rupture, we're gonna use the smallest thickness as long as they are made of the same material. Sometimes combination of different materials could be tricky, but if they are using the same material for everything, the smallest thickness is the one. Any other question? Okay, look, I'm tired, but we're gonna continue tomorrow. Is there any questions, anything? I'm gonna stop it here. I know you have to go drive to another class. What is the schedule for tomorrow? Tomorrow, the same time at 10 o'clock. At 10 o'clock, I'm going to solve one problem, one voltage connection. And on Monday, at 10 o'clock, I'm going to answer all kind of questions because you're going to be almost ready for the exam. I'm going to answer all kind of questions. And the exam is on Tuesday at 7 o'clock, one question, 8 o'clock, the other, 9 o'clock, the last one. And remember, you need to upload it because if you don't upload it, bad luck. We offer the course again in the summer. And you have to remember that you and only you is going to be solving the exam. And you have to have your camera on so I can see you working. And the microphone is going to be off the day of the exam. Any question in the chat. Anything else? I'm going to be available the whole week and weekend to help you if you need help. And we have like 5 minutes before the start of the test to print it out so we don't waste time. Man, that doesn't take more than 5 minutes to print. Everything is considered. When I design the exam, everything is considered for you to print. And if you don't want to print, I'm gonna have in the screen the exam. Any other question? Can you put more? Can you put more on exam? I'm gonna look for but to see what I have. Okay, didn't know. We turn a PDF or OneNote. You can turn a PDF as long as I can read it. You upload a PDF or any way that you can upload it, but make sure that I can read it. Any other question? Okay. Well, I'll see you tomorrow. Bye bye.